Midterm 2. Very well you did again. You did again very well. The average was 94 out of 120 points, which is 78.4%. And so that was pretty good. There were a total of how many students? Let's see. You can see it, 933 or so, 938 students that participated. And there were some questions where people were guessing, okay? And you can guess again. So take out your iClicker, please. And also the people there on the sides, you need to move into the auditorium here. I can't have people at the fire marshal who's going to close me down, okay? This is the fire exits, they need to be absolutely free. Of course, you're the first ones to run away then, okay? Never mind, I have to say that. You need to go and sit in the middle. So, let's calm down a little bit. I know you're all excited about all the good scores that you had. And I need total silence before I can continue. No talking to each other. I trust you, you all signed the honor code. And if this means something to you, then so be it. So let me see if I can give you a question. And the question will be, and this was a simple one, but you need to know your stuff. Okay, how many of the following molecules are polar? 1, 0, 1, 2, 3, or 4? You have 1 minute to answer the question. No talking, please. Of course, you can't do this in 1 minute if you don't have thought about it, because you need to VSBER, you know. What was it? So the score showed me that many of you guessed. Didn't go through the VSBER. Okay. So what's the answer, you think? C is the answer. There are 3 are polar. You really sure about that? 2 is polar. You're sure about that? I think you're not right. This is definitely not polar. This is not polar. And this is not polar. That's the only one that is polar. Okay? All right. So we can discuss this with you in the open office hours. We can discuss it in my office hours. VSBR. Okay. Let's calm down. It's not the end of the world. This is cream of the crop. That's all there is, you know. So, okay. I've never seen so much exciting for 3 points. Okay. Now let's close this up here. And let's get the iClicker started. So this time, the score will be posted this afternoon. And you will get also your Scantron, a copy of your Scantron, which will be given to you. Pointer to icon. Pointer to icon. There's somebody in my system. Okay. Where is it? It's behind there somewhere? What a great program, huh? No, it's not behind. Never give up. There it is. Oh, wonderful. So start the session, and then we can close this here, and we look at our today's session, and we start with what we have discussed the last time. And this will be on the next midterm. And in the final, of course. The final is everything. Everything you know. I'm afraid to touch this here. Okay, so. That's a German word thing, so, okay. Anyhow, we had talked about the kinetic theory of gases, and you've seen that the kinetic energy of an ideal gas only depends on the temperature. And we have derived this. Okay, why this only depends on the temperature? Because if you have a small mass, then at this temperature you have a high velocity, and E 1/2 mv squared is the same. Then if you have a heavy mass, and they have a lower velocity, and you've seen this at the very end with these little steel balls. Okay, so the kinetic energy is 3/2 RT for 1 mole, and if you divide it by this R, if you divide this by Avogadro's number, I get a new constant that is called the Boltzmann constant. That's all there is. I don't want to write R divided by Na, he found out. The average kinetic energy of 1 molecule in a gas is 3/2 kp times T. All right, and then we talked about the root mean square speed. That's of course, this is the velocity. And this, of course, depends on the temperature and the mass, the velocity. And this is the square root. This is for 1 molecule or 1 atom is 3 kb. That's a constant times T divided by m, and the whole square root of the whole expression here. Or for 1 mole, it's 3R times T divided by m, the square root of m. M is the molar mass then. Okay? And then we talked about the distribution of speeds, and I will talk a little bit more about this before I go on to what I want to discuss today. So we have seen the distribution of speeds here. You can have, would that be a heavy or a light particle? You don't know, could be anything. Okay? Now, that would be definitely a low temperature situation because you have a low speed, and this is the distribution function, which we call the Maxwell-Boltzmann distribution function. I'm plotting this here against the velocity. Somebody here, okay? Against the velocity in meters per second. That's the velocity, and this is the function here, okay? The function. And so you get this distribution of speeds at a low temperature. At higher temperature, of course, the speed's increasing, and it looks like this here at higher temperature. You see, they have more of them have higher speeds, and even higher temperature goes even flatter and further out, and that's in your book. And so if I now say this would be a heavy or a light, one of them could be a heavy, and one of them could be a light mass particle. Would that be the heavy one, or this be the heavy one? Which one is the heavy? Red is heavy? You sure about this? The heavy ones have large mass in order to have low velocity to impart the same kinetic energy than a light particle that must have higher velocity. Okay, so that means you have a low mass situation would be this here. That would be a low mass. So that would be a high mass. A heavy particle situation would be the blue, and the red would be a low mass situation. Of course, it has the distribution, the velocity distribution or the speed distribution has to be much higher in order to have the same kinetic energy. So this is the Maxwell-Boltzmann distribution. And so I asked you this question, and I think you answered this at the end, didn't you? Okay, so why don't we just go through this again that you have understood this, because some people came afterwards and they didn't understand it. So we have that Maxwell-Boltzmann distribution at 300 K, that's a fixed temperature for bromine, that's this here, okay? And then we have another molecule, bromine is Br2, okay? Then we have another molecule, or gas molecule, or atom, it's an atom in this case because is the question, they're monoatomic. What is this here? And so I gave you that hint, 1, 2, 3, no, 0, 1, 2, 3, 4. So what happened to the velocity of that new particle, or that new gas molecule? And with this you can answer this question. And just for the heck of it, let's see how many answer this right now. Okay, go give me your answer, you had discussed it the last time. And so your equation is somewhere here, isn't that right? Must be somewhere here, okay? What happened to the velocity? What happened to the velocity? It doubled, okay? What has to happen to the mass that we still have the same root mean square speed? No, not the same root mean square speed. That this root mean square speed applies, I'm sorry. So there's your equation here, okay? The 3r you can forget, that's a constant, okay? So you have what? You have double this here, so what has to happen somewhere in here? And then you have to remember this Br2, okay? Everybody has it right now. That's my success meter. Good, you remembered and you understood. Okay, good. Yeah, the equation was this here. So this here doubled. The root mean square speed doubled here. Okay, in order to get this here, you have, so this is twice, 2 times VRMS is this here. So bromine and X, okay, twice the speed here, the root mean square speed doubled. This is your equation. So if you double this here, the mass has to be 1/4 of this. And 1/4 of bromine is 80. That must be 20, isn't that right? No, bromine is 160, okay? Bromine is 160 and 1/4 is 40, okay? So that means argon. And it's 1/4 of 160 is 40, that is argon, just for those who didn't have it, okay? Now we're going to talk about real gases. I'm going to confront you with reality. That's very unpleasant, isn't it? So real gases behave sometimes like ideal gases and sometimes like real gases. So let's have a look how ideal gases behave, and we have done this. This was P times V. What's this guy's name? P times V is a constant, and this is Boyle's law. And we see the compressibility gets smaller and smaller and smaller if I increase the pressure. So I have my piston here, and this is closed here. Here's my gas. I'm at pressure 1 here. I put pressure 1 on there. I have this point. That's that volume, and that's the pressure that I'm exerting. Or that's exerted back here. That's the pressure, okay? Now I'm going to push a little bit more, increase the pressure. With this, the volume decreases, okay? The pressure increased from here to here. The volume decreased, okay? Volume went from here to here. This is 0, okay? Now I increase the pressure some more. What happens to the volume? The volume decreases even further. But now I need a lot more pressure in order to have any volume decrease, because the compressibility getting smaller and smaller. This is the quotient here of delta V over delta P. And so the third one would be, the fourth one would be here, the first point, and so on. And actually, I never reach a volume of 0 because it's asymptotical. And with this, you see that is a behavior of an ideal gas at a fixed temperature. Yeah? And we have P times V is a constant, and we know what that constant is. I have derived it for you the last time. And so the compressibility decreases. We see that it gets harder and harder to compress that gas. Now this would be at a different temperature, and this would be even at a higher temperature, okay? So they are all the same, but each temperature has a different curve in this P times V diagram. So now let's talk about a real gas. So let's see you have a real gas here, and you have a certain pressure on it. It's the counter pressure. It should be the equal, because otherwise it would collapse. And so this is point 1. Now I'm going to compress it. I get a smaller volume. I change the pressure from here to here, and I get now the volume reduction from here to here. Okay. So now remember, I have a real gas. Now I start again, putting some pressure on there, and suddenly that happens. Whoa. I pushed it, and suddenly I could go, I get all this, I didn't have to put any pressure change, and the volume changed. You see that? The volume reduced. In this point here, the volume reduced. If I go on after this point here, and put more pressure on this, then I get again a sort of a behavior like the Boyle's curve. So, but I have a volume reduction here. How can that happen? I get some free pressure change, and I get a large volume reduction. I didn't do any pressure change. You see that? The pressure didn't change here, but I get a volume reduction. Anybody any idea what happened to that gas? It's a real gas? Go ahead, loud, yell it out. No, if it's solid, it's even harder to press, okay? Let's go the other direction. You jump from gas to solid. So what? Liquid. So a gas has a lot of space, needs a lot of space. The liquid suddenly condenses, and it needs very little space compared to the gas. Suddenly you have all this empty space there, and so you can push the piston in, and you get that volume change, but you don't need any pressure. We've seen this with the crushing of the cans the last time. That's essentially the same. There was a phase transition, a phase change. The gas changed from the gas phase into the liquid phase. And with this, it occupied a much, much smaller volume. And so you had all this empty space now suddenly, and so you just push the piston. There was no pressure against it. Once you are at the, let's say this is water gas or steam, and the steam condenses, and now you have just water there. Now you press against the water there. Of course, you need to press hard again to compress the water. That behaves now like water. Okay? And so this is what we see. This is a real behavior. And that's the difference between an ideal and a real gas. Real gases have phase changes. And these phase changes, they are dependent on the pressure also. Okay? The pressure and temperature. So for another gas, it would look like this here. This becomes, no, for the same gas at a higher temperature, would become like this here. So what would that mean? That there is very little, hardly anything that can condense anymore because the temperature is so high. Now if I go even higher in temperature, then I can press on this gas, and it will not condense. So this is the temperature above that critical temperature where this phase change occurs. There are gases, and all gases, if they're above a certain temperature, and this is called the critical temperature, they behave ideal. There is no phase changes, and now you have the ideal gas law you can apply again. The critical temperature is the temperature below the gas behaves non-ideal or real, there are phase changes, and above it behaves ideal again. So any real gas has a temperature. Above this temperature, the gas behaves like an ideal gas again. Below the temperature, it behaves like a real gas, and you have phase changes. Okay, let's think about this a little bit. So an ideal gas doesn't have any phase changes, is that right? It's an ideal gas. So which is true of the critical temperature, Tc, for any real gas? The critical temperature for any real gas is smaller than the critical temperature for an ideal gas, is equal to the critical temperature of an ideal gas, or is larger than the critical temperature of an ideal gas. Does an ideal gas have a critical temperature? Okay, why don't you start answering this? You need to think a little bit about this. Oh, discussion section already. Okay, good. I brought the stuff here, okay? Alrighty, that's nice. There's 451 people here. Is it raining outside? No, huh? Don't be surprised. Yeah, that's about right. Okay, so of a real gas, the critical temperature, you compare this to an ideal gas, which is true for the critical temperature for any real gas. Is it larger than the critical temperature for an ideal gas? Is it equal to the temperature of an ideal gas? Or is it smaller than the temperature of an ideal gas? Okay? I can't give you more than this, but this is the whole point of that exercise, that you start discussing it with yourself, not with yourself, with each other. You can also discuss it with yourself. What is it? Yes, exactly. So the question is not that stupidly worded, actually. What is it? No. Okay, excuse me. I will make it till the end of this lecture, don't worry. So, does an ideal gas have a critical temperature? No. So if an ideal gas doesn't have a critical temperature, what is true then for the critical temperature of a real gas? It has to be above, okay? Above critical temperature, a gas behaves ideally. Below, you have real behavior. Ideal gases behave ideally at all temperatures. There is no critical temperature, okay? And with this, the answer was this one, okay? So you understand now, there is a critical temperature. Above that critical temperature, the gas behaves ideal, okay? For each, any real gas, that might be a very high temperature, but let's see. Look at the vapor pressure of water. Vapor pressure of water. So we have P times V, good old Boyle here, and this is the ideal behavior. That's above a critical temperature. And we come to the critical temperature. This is where this behavior starts, where there's condensation. And now we're looking at water at, what would that be? That would be water at 100 degrees Celsius. This is 273 Kelvin. Okay, that's boiling of water. What would be the pressure here? 1 atmosphere, exactly. Boiling of water. So there, of course, you have real behavior. Of course, you have real behavior at 100 degrees. The gas is steam, and it's in equilibrium with your water. Okay? So there's a perfect equilibrium, essentially, if you don't let it escape. And so if you have an open water pot at this room temperature here, the vapor pressure on top is, of course, much less. The vapor pressure on top of this is, let's go, at 25 degrees, that's what we have here, it's a little cooler though. That's just 31/100 of an atmosphere, very small pressure, okay? That's why the air, the water doesn't evaporate. That's why you have to heat it up to get it evaporate. And, of course, there's a little bit of vapor pressure above a 25 degree Celsius temperature solution, and it's 31/100 of an atmosphere. That's the equilibrium pressure of water at room temperature, okay? And so you see that behavior, that's the water. There's water vapor in equilibrium above the solution with this. So, why is that? Let's do an experiment. Let's do some critical pressure and temperature. Let's do some pressure experiment. Okay. Oh, sorry, I need carrot. Okay. You coming out here or there? Who is for here?